All right, let's talk about different types of waves. The first type of wave that I want to talk about is a transverse wave. And a transverse wave is one where the motion is the motion of the wave, the way the energy is traveling is perpendicular to the way the particles are moving. In other words, if I look at this wave here, the string, the motion of the string or the energy is transmitted that way, transmitted from her hand to the wall over here. Yet the string is moving up and down. So you can see that that is perpendicular to the motion. That's a transverse wave. Transverse waves are ones where the medium moves at perpendicular or right angles to the direction of the wave. And then we have longitudinal waves, and sound waves would be an example of those. Longitudinal waves are ones where the particles oscillate parallel to the direction. In other words, if this is the direction of my wave, the particles move back and forth this way. Remember, a transverse wave, they would have moved up and down. But in a longitudinal wave, they're going to move the same direction. That would be an example of a longitudinal. And you can do that with a spring. You can make both kinds. So here, you can see that the particles are moving up and down, and on the second one, you can see that the particles are moving, in the same direction with it. So here you have this. Here's the wave, the compressions as it's moving this way, and this spring is just going to move back and forth like that. In this one, the spring is going to move up and down as the wave moves this way. Now, whenever you talk about waves, you always get to talk about interference. And interference is when two waves meet. And different things can happen. And typically when they meet, if you have kind of a constant wave traveling and they meet each other, you're going to get this interference pattern. And what's going to happen is the waves are either going to increase, they're going to decrease, or they're going to neutralize themselves as they meet. And you can have what we call constructive interference, where two wave crests meet, and when two wave crests meet, you get an even bigger one. Okay? Or you can have destructive interference, where a crest meets a trough, and what happens is you get this for kind of the balance. It kind of cancels itself out as you go and do that. So here's an example of constructive interference, and notice that here we've got this crest. Crest is right here, meets this crest right here. So we're going to add those two parts together, and then you get a bigger crest right here. Notice here's my trough, here's my other trough. I'm going to put those two together and get an even bigger trough over here. On the other hand, if they're just slightly off, where now the crest of this wave matches up with the trough of this wave, they will cancel each other out, and what you're left with is pretty much no wave whatsoever. So when waves are out of phase, what that means is the crests overlap with troughs of another wave, and the amplitude becomes zero, if assuming they were exactly the same. And this is pretty easy to see in water, that you can do this. And if they are in phase, then they are twice as big. Now, what I would like you to do is I want you to take your iPad and I want you to look at the app, and the app is called Ripple Free, and I believe you should have it on there. And just go and take a look at it. It is a very simple thing. It kind of shows me some different waves. You're going to see some interference waves. But just start off, and if you look at it, you'll see it says there are different things like single source, two sources, and just kind of go through the single source, and the two sources are the ones that we should be looking at right now. And you can start that wave, and if you want to, you can actually create interference by just touching the wave, like if you just touch the water and with your finger, you can do that same thing, and you'll see kind of an interference pattern that forms between that. And I believe in general when we talk about this, and if we were to actually use real water and lights and stuff, the dark waves are actually the crests, and the light is actually the trough. but it doesn't really matter. But just look at what happens when you create two waves and they meet each other. Or if you're done with a single source, just go into the next one and you'll see two sources that meet. And notice how you get this pattern, just like what we see on the screen here. You get this kind of pattern that's formed like this right here. And why did I not get my screen? I need to... Why am I not getting this? Escape. Let's start that again. So I can write. P. So this is what I'm talking about right here. And notice how you get like these lines. Kind of just go right down there. And that's because in those areas, usually what we're seeing right there is where waves have canceled each other out. So we're getting, if you were to look at it, if this were real water, you would see that those are flat areas. These lines right here that they've got through there. So you got crests and troughs that meet, and you get this kind of different interference pattern as you go through them. So you can play around with that on your iPad for a little bit. Here's just another thing. You've seen those paper or those, you know, like sheets of plastic, whatever, that they have curves or circles in them, and if you turn it, you get this pattern. And I'm not exactly sure how you pronounce that, moire pattern or something like that. That's another example of interference. And all waves distribute or show interference. Light waves, sound waves, everything. Alright, so let's talk about a standing wave. Standing wave is where we get a wave to actually look like it's standing still. And we can do that if we create a wave that has just the right wavelength. It looks like it's just not moving. And actually what it is, it's moving, but you know, it just happens to be traveling back and forth at the right amount of time that the rope itself may not move or something. And you can get certain parts of it to be perfectly stationary. Those parts are known as nodes. And then the parts where it moves rapidly would be known as antinodes. The antinodes are always halfway between the nodes. And they're the result of interference. What happens is the wave travels down, hits the other end, comes back, and you get interference. And the nodes are destructive interference. And the antinodes would be constructive interference. And let's take a look at this picture. Let's kind of analyze this a little bit so you can kind of talk about what they're looking at here. So here she is. She's swinging her rope. Okay, she's swinging her rope up and down, and this wave has traveled. It's gone this way. It hit here, and then it would reflect back. So that's what they're trying to show you here. So the wave travels down, comes here, and it's going to be reflected back. And when it's in phase, those two parts of the wave will build on each other. So, you know, the crest will have met another crest, or trough will have met another trough, and it kind of builds on that. You can also do it in such a way that they counteract each other. So if they're out of phase, then the crest will meet a trough, and so right here, and they'll cancel each other out, and you basically get nothing. You know, it wouldn't go anywhere. And you can show down here, if we just keep sending multiple waves. So up here we were talking about sending one wave, I believe. But here she's sending a whole bunch of them here, and you get this. And this is pretty easy to do with the rope, and you can shake it so that you just get this area, this where that moves up and down, and this part that pretty much just stays where it's at. This part moves up and down, and so on. And you get this, what looks like a standing wave. It doesn't look like it's going anywhere. And that's what they're talking about. And you can produce a standing wave when you have, when you produce the frequency that is exactly the same length as the rope is, or double that or triple that. You can do it anytime you find one standing wave. If you double or triple the frequency, you can find other ones. So here's, in this example, they have the standing wave where it's half a wavelength. In other words, this is what they mean by half a wavelength. Here's the crest. When it reflects, it comes back down here. And this wave would just look like this. It would just travel this way and travel back all the time. Okay? So that's half a wavelength. The total part of the wave would be this far here and this far back. Or you can do it where it is one wavelength. So in other words, one wavelength, I've got, here's my crest, it goes all the way through the trough and back to the middle. So we're back at the same point. That is one wavelength, the entire part of the wave. And then returning is one wavelength. So if I do it at half the wavelength, I get a standing wave. If I do it at one wavelength, I get a standing wave. And I can do it at frequencies, twice that, 3 times that, and still get more standing waves if I want to do that. So I would get that down there. And you get standing waves all the time. We just don't maybe know what they are. But when you pluck a musical instrument, something with a string, that's a standing wave that you get. The wave is designed to make that. Or if the air in a pipe organ, or when you blow the air across a soda pop bottle, you actually get a standing wave in that way. You can have standing waves in both transverse or longitudinal waves. Doesn't really matter what type of wave it is. All right, so here's a question. Is it possible for one wave to cancel another wave so that the combined amplitude is 0? Well, of course. This is called destructive interference. And so, yes, you can do that.